We're now going to look at, in the next example, a third-order Cauchy-Euler differential equation. Again, to notice that this is Cauchy-Euler, you'd want to check to make sure that the power of x in front of each derivative matches the order of the derivative. So x cubed, third derivative, x squared, second derivative, x to the first derivative, and then just a constant term times the function y equals to 0. Because it's Cauchy-Euler, we can solve it the same way by assuming that y equals x to the m. We would then want to go ahead, I'm not going to show the work for this, but go ahead and then calculate the three derivatives of y and then plug them in. If we do so, we would get x cubed times, we're going to have m minus 1, m minus 2 times x to the m minus 3, that's the third derivative, plus, not now, this is one where I really need to make sure we have full room because this is going to be a lot of writing. Please cooperate, Microsoft. Okay, there we go. Plus 5x squared times the second derivative. That's going to be m minus 1 times x to the m minus 2 plus 7x times the first derivative. That's m x to the m minus 1 plus 8 times x to the m equals 2 to 0. And I'm going to skip a little bit because we do know ahead of time that when you multiply all these x's out, every one of these terms is going to be an x to the m term. So I'm just going to cut to the chase and factor that out immediately because it will factor out. And now here's what we're going to be left with. We have an m times m minus 1 times m minus 2. Here we're going to get a 5m m minus 1. And then from here we're going to have a plus 7m times x to the m equals 2 to 0. So that's going to be our auxiliary equation this time. We're going to set this thing equal to 0. Let me first distribute the m in. So I'm going to have an m squared minus m times m minus 2. This is going to become plus 5m squared minus 5m plus 7m equal to 0. Let's expand this. You would get m cubed minus 2m squared minus m squared plus 2m plus 5m squared minus 5m plus 7m equals to 0. Combining like terms, we have m cubed. Negative 2 minus 1 is negative 3 plus 5. Negative 3 plus 5 should give us positive 2m squared. That takes care of all of these terms. And then 2 minus 5 plus 7. That's going to be negative 3 plus 7, which would be 4. And then I realized I forgot this little guy over here. Don't forget him. Plus 8 plus 8 plus 8 equals 2 to 0. Now, this is one of those things where we now have to solve, this algebraic polynomial. There's many ways you can kind of do this. If you remember, if you had like a really good college algebra class, factor by grouping actually works on this one pretty nicely. If not, you would want to, do more things like the rational roots theorem and whatnot. And I'm not even opposed to y'all using technology in this class for something like this. We're trying to solve differential equations, not necessarily have to invoke crazy algebra. Let me show you the way to do it by hand, because we can actually work this one out pretty nicely. And then I'll show you maybe how, if you get stuck with something like this, you can use technology when trying to solve third-degree algebraic equations or higher. But I can do a factor by grouping. Pull an m squared out of the first grouping, we get m plus 2. Pull a 4 out of the second grouping, we get m plus 2 equals to 0. And then m plus 2 is common for both of them. So we can go ahead and factor that out. and we're going to get these as our roots. We get m equals to negative 2, subtract 4, take a root, m squared equals to negative 4, m equals plus or minus the square root of negative 4, that's plus and minus 2i. So that's the complex conjugate pair with an alpha value of 0 and a beta value of 2. And now we're ready to write down our solution. Before doing so, let me kind of show you a way you can solve this. So if you get stuck, one of the ways you can do this is graphing. And oftentimes, especially with third degree polynomials, if you can get one root, you can get the rest of them. So I could graph this auxiliary function. I could call it m cubed, just trying to remember it, plus 2m squared is plus 4m plus 8, yep, because it factored. And at the very minimum, at least what this would do is, remember, this one actually only had one real root. It had the real solution negative 2. So if you knew, and you would see this from the graph, graphically, you would know that negative 2 would be a root of this polynomial. And then from algebra, the factor zero theorem would say the following. So hopefully you all remember this. Probably haven't had to use it in a while. But, give me 1 second. It's kind of freezing up here on me. But if C, I probably won't be able to write it, but the root factor theorem says the following: if f of c equals to 0, then f minus then x minus c is a factor. So you could do polynomial division, dividing by m minus 2, which would be m plus 2. Do polynomial division, that would break it down into a quadratic, and then you could use quadratic formula to find the rest of this. Okay. But since we have everything else that we need, and it's really frozen, that stinks. Anyway, so we do have our roots. I'm just going to cheat. Somewhere here it is. But I wasn't able to plug it back in for showing it. But the one root we had, the real root was negative 2. So we get c1 x to the negative second plus, and then for our complex number, remember it's usually out in front we would have an x to the alpha. But since it was plus and minus 2i, the real part of those complex numbers is 0. So we get x to the 0, which is 1, so the x portion doesn't show up. And then it's c2 cosine of beta ln x, where beta is 2, plus c3 sine of beta ln of x, where again beta is 2. So this would be our third order Cauchy-Euler equation solved. Nothing different than what we just did. The only thing that becomes a little bit of a nuisance sometimes is, whenever you work with third degree order Cauchy-Euler differential equations or higher, then that involves solving third degree or higher polynomials in the variable m. That in of itself is not always easy to do. Oftentimes you may need to use things like technology, or if you're very good at algebra, things like the rational roots theorem, or some fancy factoring methods like grouping like I just did, in order to be able to break them down and to find the roots.